afternoon, everyone. My name is Gavin Fields, and I'd just like to welcome everyone to today's webinar, Hydrology 101 by XP Solutions. Again, my name is Gavin Fields. I'm a Senior Water Resources Engineer here at XP Solutions and provide assistance where I can. And today's webinar is focused on hydrology for Asian regions, and I'll do my best to cover content that is relevant to the many countries that XP Solutions supports. For those who may be unfamiliar with XP Solutions or new to our products, it's a simple overview. XP Solutions is a software company. We are based here in Brisbane in Australia. We also have offices in North America and Europe, and have presence in South America as well, with distribution in your relevant regions across Asia. And why XP Solutions? XP Solutions is a great tool to support engineers like myself in the stormwater space. It has a very good graphical user interface to analyse both 1D hydrology, 1D hydraulics, 2D overland flow using the shallow water equations, and we have a range of products, and there's just some icons at the bottom of the screen for XP Storm, which is a hydrology hydraulics package, XP Rafts, which is pretty much a pure hydrology tool that is used widely across Australia and Asia. XP2D is the module for two-dimensional surface flow, and XP Swim, which is really the parent product for the company, and it encompasses pretty much all of those features in one generally easy to use package. So for today, I'm going to cover the physical characteristics of hydrology, talk about climate in Asia. I have travelled a fair bit across Asia, and my experience is getting better, even though I am Australian. Talk about precipitation and the relationship between analysing real-world historic storms and also converting those to design storms. It's always good if in your region you have design storms, but sometimes we have to work those out ourselves. Discuss catchments, the most important part of hydrology, some routing methods, looking at results, and I'll also do a live demonstration inside XP Swim today. So I'll try and talk for as quick as I can, and then we'll spend some time looking at how things can be done very rapidly from scratch inside the software. It's always a great way to see how quickly things can be done using a tool like the XP Solutions products. So hydrology. Obviously, it's a long sentence there, but generally speaking, hydrology for engineers is about converting and assessing the impacts of rainfall when it hits the ground, and how it can be calculated, determine hydrographs, and move down creeks, overland flow paths, pipe networks in urban areas, and again, really trying to quantify how that flow then moves from one location to another. And so what are some applications of hydrology? Well, the applications of hydrology are many and numerous, and obviously the most important ones, particularly in developing areas, developing countries, and even more so for fully developed countries, is assessing irrigation for agricultural purposes, water supply, flood control if you have issues, and obviously flood control includes structures like dams, weirs, and other critical assets. And sometimes that water can be used for hydroelectric purposes, usually on the back of a dam. The capacity of storages at structures at reservoirs is a very important function, also goes hand in hand with flood control. And at different locations around Asia, seasonality is a very important factor. And how do flows occur in summer versus winter, or autumn and spring, how does that affect particularly agriculture? How does that affect growing food? Very important functions. What are the impacts on infiltration, for example? Moving your hydrology forward, again assessing those structures. And bridges. We obviously don't want bridges to wash away. And so why is hydrology important? Well, again, we talked about those in that previous slide, but functionally agriculture is a primary reason. Planning, town planning, we want to protect our population. Engineers across the globe have a core obligation to protect their local population, and hydrologists sometimes don't quite get the respect that they should or deserve. Sometimes when floods beyond our estimation or control affect our populations, but on day-to-day work, hydrologists are one of the most important professions in the world, so everyone today can pat themselves on the back for being interested in hydrology. And then we get into development. Sometimes that's where most of the money comes from for us, but it's assessing change. What is the impact of taking pasture land or farmland and converting that to urban areas for people to reside, or commercial and industrial precincts or factories, etc. Lots of money in that space. Hopefully everyone is very familiar with the hydrologic cycle. I won't hold point here, but obviously rainfall converts to runoff. There are a number of processes in here, and many of these can be modelled numerically inside computer programs such as the XP Solutions tools. And let's get a bit more specific. Asia, just north of Australia. Australia presents itself in that very, very bottom right-hand corner of the screen, and on the east or the right-hand side of this image we have the Pacific Ocean, the Indian Ocean to the south. We have the South China Sea, the Bay of Bengal, the East China Sea. All of these major water bodies have very, very strong impacts on the hydrology of this great area called Asia. Not just the tropical island areas near the equator, but all the way through to the north, North China, Mongolia, those places. Hydrology is the lifeblood of, and the supply of water is critical to supporting the populations. Lhasa in the middle of the screen. I wasn't too far away from there a couple of weeks ago. I had a very enjoyable trip into China, and you can very quickly see, if you travel the great expanses across Asia, the change between the tropics, the semi-arid desert areas. If we go north of Beijing, incredibly dry in summer at times, very cold. I think if there is anyone watching from China at the moment, Beijing is probably something like minus 17 degrees right now, so very, very cold and inherently very dry as well. Asia is an interesting area, as is North Australia at times, because of monsoonal effects. And monsoonal winds can really impact our climate a lot, and the relationship around, particularly the Bay of Bengal, is a very important part for India, and how storm systems then persist and are held up by the very great mountain system that leads up towards Mount Everest. And these systems are generally predictable. They can provide huge amounts of rainfall, and to the northeastern precincts of India, this little map here shows depths of rainfall per year approaching 4,000 millimeters of rainfall, and a lot of that falls very quickly in short periods of time. And so flooding in those regions is very, very important, not only to protect the local residents and citizens, but also for agriculture. Because what happens with those excess rainfalls, we lose sediment. And those nutrients that are in the sediment will flow down river systems. We then have our sediment beds downstream, and that can be very good for agriculture. So sometimes there is a benefit from the difficult times that are sometimes created from rainfall. This is an interesting review of the Philippines, further to the east, sort of the eastern extent really of Asia, and typhoons. Typhoons are quite a bad thing, and hopefully everyone can see that hopefully all the electricity is turned off in this particular photo. This particular image on the left-hand side is the track path of only just a couple of years of typhoons in and around the Philippines. And sometimes they can affect multiple countries because the space between the Philippines, Japan, China, Taiwan is not very great, and typhoons then become multinational issues. Malaysia, just to the south and west of the Philippines, and obviously east of India, rainfall maps like these are provided by the Malaysian government for both East and West Malaysia, and they've used this information to help define their IFD information, their intensity, frequency, duration patterns, and this sort of information is done in most countries. I've seen this sort of information for places in India, obviously Malaysia and parts of China, Japan, Korea, and definitely Australia. Australia has these maps as well. So rainfall. There are a number of ways of assessing rainfall really for design purposes, and sometimes just simply for assessing real-world events. It's always, I think, a bit of a privilege to actually assess real-world events. Not a lot of engineers actually do model real-world storms. It's sometimes hard to get reliable information, and one of the most important pieces of information that you need for the assessment of a storm, be it last week, last year, last decade, 100 years ago, is the reliability of that precipitation data. And without good rainfall data, then you're going to be pretty stuck for your assessment. But if you have a good rainfall record, and most countries these days are starting to invest more money into data capture, record keeping, quality assurance, we can start to use that to build design storm information, such as on the right hand side, and we can do statistical analysis of that data set to start to predict what is the impact of, for example, a 1 in 100 year storm, that 1% event. Different countries use different terms, so Australia, for those who are not familiar, really is moving away from average recurrence interval as a terminology point. It's now moving to annual exceedance probability. They're functionally the same, but makes it very difficult for the 2-year event, which unfortunately is something like the 63.4% AEP, but that's just statistics. And of course, with that design storm, not only with the rainfall data, but we would need to derive a statistical temporal pattern or representation of a real storm to analyse and design our infrastructure, assess risk, and be consistent from one project to the next. That's one of the advantages of design storms, to be consistent. And that is a very good thing as an engineering group, to be consistent. So yeah, just quickly talk about AEP and RO. I've one in front of myself there. But obviously the reason that this terminology is changing is really misrepresentation. There's nothing worse than the media, newspapers, or the general public being told a recent flood was a 1 in 100 year event, because they may believe that could be that there's another 99 years before the next one. And of course that's hopefully everyone in this crowd, people listening, watching this either today or in the future, understand that yes, when engineers use terms like 1 in 100 years, it does not mean that it can't happen again next week or the week after that. It would simply be unlikely. It would be unlikely. So catchments, in my opinion, not only with simply rainfall, but catchments are the most important function of hydrology. What is the shape and characteristic? Do you have a highland region falling down to an upper floodplain? Is there a dam in the way? Do we then have a prolonged river? And if people have been particularly to north and east of India, there are a number of modified rivers and irrigation canals that have really, in a way, altered the alignment of the river systems, mainly for agricultural purposes. And if we can maximise the use of our precious resource called fresh water, then I think that's fine, as long as it's not to the detriment of someone else. And ultimately, our water generally gets to the ocean, unless you're in isolated catchments with strange low points. In Australia, one of the biggest catchments does not drain to the ocean. It drains to an area of land that, when it dries out and becomes a salt pan, is 10 metres below sea level. It's very unusual, but a wonderful place if you ever come to Australia to go to Lake Eyre. It's called Lake Eyre. Catchments vary in scale. I'm sure not many of the people in today's crowd would be interested in catchments of quite this scale, but modelling the Brahmaputra or the Ganga catchment or the Indus to the west of India, these are huge catchment areas. Most of us will probably work at a much smaller scale, tributaries, rather than regional catchments like this. In Australia, we have a catchment that is probably of similar catchment scale to the Ganga, the Ganges river, being the Murray-Darling system. It's about 1/7 of Australia. And yes, there are models of that particular catchment for very good reasons, particularly for, again, agriculture, water rights, distribution for farming. But yeah, catchments can start very large and can obviously go to very small. Could be your backyard. You may only be interested in what falls on your roof in your backyard and how does it get to the street. Very small catchments. Numerically, when we think about catchments, the key data parameters that we need is obviously that area. We need to define our boundaries, look at our high points between our low points, the interfluve, if you want a technical term, and then look at other parameters. Different hydrology methods need things like slope, potentially the length of the catchment, the width of the catchment. Internally, what is the use of the existing catchment? Does it have a high fraction impervious? And be that because of existing development or because it has a very rocky terrain. Rocky terrain is just as impervious as concrete, of course. And then what kind of surface storages come into play? You may have, when I gave a presentation last week, the comparison for storage went from small puddles on the ground to dams. And so it's two opposite ends of the spectrum, dams to puddles. But those storages all have an impact on your calculations and affect your losses. And the typical losses, I think I've got a slide on this, include things like infiltration, losses to the groundwater, evaporation over time, pan evaporation from your dams, interception, water that doesn't even hit the ground itself, it's captured by rainforests or trees, or simple things like rainwater tanks. Rainwater tanks are becoming a very common interception device across the planet as we want to try and harvest that water locally. For more complicated assessment, there are a number of loss methods that are available, and within the XP's range of tools, these are 4 of the common ones: Horton, Greenamped, Uniform Loss, and the SCS curve number. The ones that are very common, of course, are under Uniform Loss is initial continuing, but also SCS curve numbers is very popular in the Asian region, from Korea over to India. I personally use a routing method called Lorenson's method. I'll talk a bit about that. It's used in a number of countries as well. It's used in India and Malaysia and a few other places with some popularity. And initial continuing would be my pick loss method although of course they're all very good for their purpose. And so some routing methods going beyond just the losses. And so we have our rainfall. We can route it through a numerical equation and convert it to a hydrograph. That's our real purpose. Hopefully, and I trust most people today would be familiar with the rational method. The rational method is useful for small urban catchments, in particular in developed areas, small rural areas, and different regions have different limits. Malaysia, for example, the upper limit for the rational method is only 80 hectares. If you have a catchment greater than 80 hectares, then you should not use the rational method. And likewise in parts of Australia at times that's made more flexible to as high as 500 hectares. However, in Australia, and it is quite possible that a result of a recent change to our major guideline here in Australia will influence parts of Asia, and the rational method is no longer as popular as it once was. So the recent amendment to Australian Rainfall and Runoff, and that is a free download. You can look that up. Go to a search engine on the internet and look for Australian Rainfall and Runoff, and you'll find a very comprehensive, very up-to-date guideline on how to assess hydrology, and it is very, very specific to hydrology. And it at times talks about SCS and particularly the non-linear reservoir methods, and Lorenson is one that I'm a fan of. I've highlighted there. But also time area method, which is another respectively simple hydrology option that is used in some parts of Asia. The rational method, again, everyone should be familiar. Q is flow, C is the coefficient of runoff, I is your rainfall value, and your intensity of rainfall. A is your area, and sometimes you'll use a unit conversion depending on what you use for your area, but if you work in hectares, then you divide it by 360 to end up with a flow rate at cubic meters per second. But we only really end up with one value. It's that Q peak. It's that peak value. Some methods try and create a triangular function, as shown on the right-hand side, but really that's not necessarily reflective of what the method functionally means, but you end up with a singular flow rate. It doesn't tell you how the catchment gets to that flow rate. It doesn't tell you how the catchment draws down from that flow rate. And that's a real weakness, a huge weakness to the rational method. So time area method, it starts to modify this. It takes functionally simple rational method calculations, breaks them up into a patterned scheme. You end up with a rainfall hyetograph, and that's the graph on the bottom left-hand side of the screen. You can run your equations over and over again, and still functionally very similar to a rational method scheme, and you create this what appears to be a routed hydrograph, as shown on the bottom right-hand side of this diagram. There are some limitations to this method, of course, like all good methods. It doesn't work very well with particularly large catchments. Again, anything that if we had a time of concentration, it's not a parameter I talk about a lot, but anything over 24 hours, the time area is it's not necessarily for you. So 24 hours is a bit of a limit. SCS. SCS is a bit more complicated at times, has defined temporal patterns most of the time, and runs through a series of equations to define a hydrograph, and very popular on the west coast of America, which is where it comes from, and again used broadly, but have to look at again time to peak flow. That's an important point, and that affects the initial ramp up and also the lag of how the catchment drains out pursuant to the peak rainfall. Lorenson, one that I'm very familiar with, very familiar with. It is certainly number one method. Sorry, my just bumped that there. Used very widely here in Australia, and it has an equation which is S equals BQ to the n plus 1, where S is storage, B is a coefficient and comprises of area and the fraction impervious, and also the catchment slope. So it wraps all of those parameters in. it's a bit of a complicated process. Thankfully, the software looks after us to do this quickly, and ultimately we will generate very quickly a hydrograph at the back end. This is a Lorenzon's method calculation, but I could have done this using SCS or any other method. And it shows the impact of development. And so if we were to go from a low fraction impervious, so a grassland, then we might have a graph on the left-hand side with a peak discharge rate for this small, I think it's only a 1 hectare catchment of say 0.33 of a cubic metre per second. And when we develop it, we make the catchment more impervious. The rainfall responds completely differently. The lag is different, and it responds quicker, it drains quicker, and of course the peak flow rates change rapidly. When we look at long duration modelling, infiltration is a very, very important parameter. We can lose large sums of water through infiltration. This shows blue at the bottom. And the interesting one that I always like looking at on this particular data set is that this second storm here is the smaller storm with the peaky storm before it, generating almost no runoff because it's picked up in losses. The catchment was dry, had that dry period for certainly a few days beforehand, but it's that second storm that followed the first one that actually creates the big discharge rates. A very familiar storm that I have, I've looked at a bit here in Australia, was a situation where there was 2 cyclones in only a couple of weeks. So the first cyclone didn't really do a great amount of damage, but it wet the catchment. The infiltration was taken up, the bulk infiltration functions, and then unfortunately another cyclone came through and really flooded the greater catchment around here in Brisbane. And that happened quite a long time ago, much longer before me, but in the late 1800s. If we have those conditions, then most catchments will be in trouble. But yeah, that's how infiltration can affect us. I'll just hop out of this. I'll go and do a quick demo in the software before we wrap up, and show you what we can do in the software. So I like always starting my demos from scratch. It's great to show a prepared model, but it's good to show how quickly we can get to hydrology in our software. I think that's one of the big advantages of why XP Swim is and XP Storm are such popular products. I'm going to start a brand new model, new from a default template. So I'm just going to hit continue here. And most of us, I believe, there's only a few countries in Asia that might consider to use feet and inches. So most of us will use metric. And I'm going to store this on my computer. I have a folder here, and I'll call this Hydro Demo. The file extension is a .xp extension. This warning is just saying it's taken a template file just forward 0.1 of a step. The current version of the software is 2016.1, and the 2017 release is really not far away. I won't commit to a date, but it should hopefully be possibly before the end of the year or very early in the start of the new year. So not far away at all. Something that I always like doing with this particular file is, and I'll minimise a few things down. I'm going to minimise my 2D model and my reporting. They go hand in hand. We're not doing a 2D demo today, so I'm going to stick with some 1D work. But I do want to look at a background image, and I'm going to add one in for a site that I'm familiar with. And this is a rural site with some urban around it, so it gives everyone some flexibility on what we're looking at. The next thing I'm going to do is load in a surface file. So I have a terrain file already, and this particular file did come from very basic XYZ data. Hopefully I've grabbed the right one. Looks like it. And I'll just convert this to contours. And to do that, I just right-clicked on the entity, went to Display Properties, unticked the fill component, and I'm going to show these at 5 meters and 1 meter contours. Hopefully we don't have too much lag today. In fact, that's still probably a few too many, so I might just send that back, and I'll just show the major contours. But we can see we've got some high terrain up and around these hills, and it flattens out as it gets down to this this plain, and this low part, which is a farm, could be ripe for development. But I'm going to use some of this upland area just as an example to work out the flows to a small creek through here. To do that, I'm going to go to my catchment utility. I'm just going to change its colour just quickly to make it a bit easier to see on the screen, and just make that blue. I'll make the size a bit bigger, just quickly. And I'm going to use my catchment tool. So we have a polygon option on the right hand side, and I'm just going to trace through some of these high points, and I'll come down through this ridge to here. I'll wrap up and around to a catchment. I kind of know this side. I'm actually missing some surface information, but we'll ignore that for today. And I'll come back around here through again my ridges. And there I have a reasonably large catchment that I've just drawn using the terrain information. Just ignore that low point at the bottom there. But I'm going to put in a node down in the channel, and I'm going to link this catchment to this node. And I always like linking my catchments to sub-catchment 5, but it depends on the method. And so for some people who have heard me talk before, I nearly always go to sub-catchment 5, but I'm going to change my tack today because I'm going to show you an SCS method, and I'll go to sub-catchment 1. And I'm going to go to my tools menu. I'll calculate my conduit, my node catchment area, and I've gone from no area to 176 hectares. So it's not too small, but it's applied that information. The next tricky thing that I have to work out in this catchment really is probably the slope. And I've picked a pretty hard place to do that because I have lots of varying slope up the ridges through this creek zone in the low contours. But I do have a ruler tool on the right hand side, and if people aren't familiar with this, the ruler does give me some options to try and calculate slopes, and it is dynamic, so it doesn't matter where I go, I can try and get my slopes. But I can clearly see that my slopes are, with the exception of the flat up the creek, and even it's pretty steep, it's 3, 4, 5%. I've got a pretty steep catchment. So for today, I'm just going to assume a slope of about 10% is the value that I'm going to put in. I'm going to double click into this node. Sorry, I'm in the wrong mode. I've got to go to my runoff mode. It's another important feature of the software. We have the runoff mode, a sanitary mode for sewage application, and hydraulics when we start to move this water around. Now that I've jumped modes, because I drew that node in the hydraulics mode, I just need to press the plus icon on the right hand side, or the plus key on your keyboard, and we can activate that. Here, now that I'm in the dialog, I can see I've got my 176 hectares. I'm going to say that this catchment has a fraction impervious of about 20%. Width is not a parameter I need to worry about for SCS, so I'm going to ignore that parameter and leave that just as 0. In the past, you had to put a value there, but not anymore. And I'm going to put in a slope of 10%, and this particular parameter by default is actually in meters per meter. So 0.1 is 10%. I can then click into this dialog, and here we can quickly talk about the routing methods that are available inside this great program. The first point is the EPA runoff method. It's very, very useful. It's used well in again in America. Kinematic wave is one that has been well documented for well over 100 years. Lorenson's method, again, could be quite popular. If you click into it, there is the underlying equation, S equals BQ to the n plus 1, one that I'm very familiar with. The next one option is SCS Hydrology, and this is where I'm going to go for today. And we need to pick a pervious area curve number. I'm not the greatest at SCS, but as a curve number, I'm going to pick a curve number of 65. I then need to calculate a time of concentration, and we have a few TC methods inside the software, or I can type in a direct number. So you can use Bransby-Williams equation, the Friends equation, a modified Friends equation. There's lots of options to work out your TC, or I could type one in, and I'm going to type in a time of concentration just for this catchment of 20 minutes. I'm going to keep this this hydrograph shape, the default, which is 484. There is lots of documentation on SCS and how this particular parameter can change, and then I'm going to go to an initial loss with an initial loss value of 0. And this is one that I'm a big fan of. You could have arguments all day long on this parameter, but for design work, regardless of the fraction impervious, I don't typically model initial losses, and hopefully that doesn't cause too much pain for people. But if we're modelling real storms, if I wasn't modelling an SCS design storm, then I would definitely put a value in. And for this catchment, a real-world value might be as high as 15 millimetres or 10 millimetres as an initial loss. But I would have to be modelling a storm from last week, the flood from last year, some historic rainfall data before I would prefer anyone use an initial abstraction value. I'm going to hit OK there. Oops, what have we got here? Okay, so it isn't like that, so I'm going to put in point 1. Okay, take that back, put it 1 millimetre, so a very low value. The next item I need to apply to the software is rainfall. I apologise on that discussion on low losses. It's a function of me being very familiar with Lorenson, which very much accepts a low loss. I'm going to pick one of the standard SCS storms, and I'm going for the SCS Type 1A storm today. And if I edit this particular storm, I can go to constant time intervals, and this is the temporal pattern, and I'm going to apply a rainfall depth at this particular location of 220 millimetres. I apologise, I did work that one out, but you could go to your local IFD data, or derived from a historical rainfall data set if it's available to you, and determine a multiplier for this graph. And this is what the storm will look like with a total rainfall depth of 220 millimetres. So I'll have a burst with a short duration intensity of 55 millimetres. If I hit OK there, that's my pattern. It's weighted around the 8-hour mark. So I need to run this storm for a little bit of time. And I'm going to hit OK, OK, select there. The next phase, we could look at infiltration. And I'm getting really towards the end of my demo here, but the infiltration, there's a few options here. I could go to an initial continuing loss or SCS. So I'm going to put SCS in here. And if I hit Add, I can edit SCS. And again, we could go to a curve number. But interesting enough, this information has already been applied up in the hydrologic, so I don't necessarily need it for SCS, but I think I typed in 65 and an initial depth of 1 was what I typed in earlier. But if you wanted to use an initial continuing loss, you would go to uniform loss, and the dialogues are very, very easy to understand. But I'll go back to SCS. The catchment Mannings values, I could change these and change the Mannings value to 0.015 and 0.045 for my catchment. SCS doesn't use a depression storage value, so that's okay, and neither does Lorenson's method. So if I select that, I've functionally now completed my hydrology for an assessment. The last thing I need to do before I can run this particular little catchment is go and test my time. I need to tell the software when and how long this is going to run for. So I go to my job control, and the only thing that I'm going to change here is really the time, and check that it's okay. So I'm just running at the start of this year, start of 2016, run it for 24 hours with a 60-second calculation time step. These values here to the left, the dry time step and the transition time step, they actually are not used in this particular model. They will only be used when you're doing historic storms and you're running those dry interstorm periods. I'm going to hit OK there and OK. Just do a quick save, and I'm going to hit run. Oh, I've had an issue there. I wonder if I've got this saved in a funny spot. That should be fine. Bear with me 1 second. That should all be fine. I must have a funny parameter ticked on here as a default, and I'll turn off another function here. So just turn off to say I'm not running the hydraulics, and I'm going to go to my I think I know what I've done wrong, but I'll just try one more time. My apologies for the embarrassment here. What it is, it's the duplication of the loss. So I'm going to turn this one off and clear this. And I can also change my methods. We have two engines inside the software. We have a 32-bit engine and a 64-bit engine. I'm going to switch to the 64-bit engine, apply a bit more crunch to things, and hit solve. That's better. There we go. It was actually the second, the duplication of the rainfall loss. But now that's run very quickly for one storm, and it is usually very quick to run your hydrology calculations. And here from our 130 odd hectare catchment, I have achieved very quickly a hydrograph of about 17 cubic metres per second, which yeah, is about right for that kind of inflow. So XP as a tool to derive your hydrology is very quick. And of course, once you've done your hydrology calculations, we could then apply this to a 2D model and take it away. And in fact, I will just show you an example of how that translates. It takes a little bit more time to run a 2D model, so I'll open up one that I have cooked before, and I will do this as quick as I can. While that's loading up, I'll just come back into here. Other parameters we can look at inside the results can be found via this little icon up to the left of the print button, and we can show our excess rainfall, our infiltration, and our evaporation. If you're in North India, snowmelt may be a very important part for you as well. That's an area I've done a little bit of work. If you have glacial runoff, and we can modify the display of these graphs and just get a bit more information from the model. Another point that I sometimes get asked is, what about the technical information from our hydrology? And to see that, we can go to our output file and just go to the browse for file, and here is my output file for this particular run. And this file is a bit lengthy, but it has good summary information on all of the parameters inside the model. And table R7, I think it is, talks about continuity and whether or not the model has lost water or not. And if your continuity is good, I have a continuity area of only 0.44%. Just implies that I probably haven't run the model long enough. I might have needed to have run this for maybe 26 hours or 27 hours instead of just 24 hours, and I might have even been able to improve that value. The water wouldn't be stored in the model. Anyway, I'm just going to browse to the model I wanted to show you as an example, and after that we'll wrap up for today. So this one here will do. And this is the same site, and I've broken up the hydrology in this one, and I've then applied it to a 2D model. You can look back at some of the other webinars that XP have prepared over time to have a look at 2D modelling, further to 1D modelling, But again, if I just zoom out, it's the same site. A few more parameters put in. We've got some catchment hydrology at the top here. But importantly, when I turn on my 2D result, here is the maximum water depth that the flows from this particular catchment produce over time. And we can get some very, very useful information. And there's that creek that we functionally modelled the input to when I distributed it out across the entire creek. Again, have a look at the 2D webinars for that particular process, and you can build together your skills inside the software very quickly. Anyway, that brings me towards the end of today's webinar, and I hope you got something out of that. I'll just duck back to the slides. If anyone does have any questions about hydrology, any questions about the software, myself and a few of the other guys will also try and answer your questions. And if there's anything more specific, get in touch with the guys. In fact, not at that XP Swim one. We'll get you to go to the Asia Pacific email address at the bottom there, which is AUSales@XP Solutions. That's probably the pick email address to use. So AUSales@XP Solutions. And once again, thank you everyone for listening in today. I hope you have enjoyed today's presentation. Cheers.